So Stephen and I's project is on the Indium-111 scan, discovering the origin. So Stephen and I both have a passion for the medical field since we were both going into careers that involve medical devices. We picked the Indium-111 scan because we both have never heard of it, so it gave us an opportunity to learn about something new. The Indium-111 scan is a very interesting medical tool that incorporates nuclear chemistry, and it allows the providers to gather great information about what's going on inside of a patient's body. So the Indium-111 scan is commonly used in medical imaging to scan white blood cells, so providers can gain an inside look at where the patient's body the cells are conjugating to help locate possible origins of disease. So like we said in the last slide, it's used to help identify inflammation and infections and stuff like foot ulcers and fevers of unknown origin. The scan works by the provider has to take a blood sample from the patient. The Indium-111 then gets tagged onto those white blood cells, and then the provider injects the blood back into the patient. Since the Indium-111 has a half-life of about 67 hours, the patient is asked to come back about 24 hours after the initial injection, and then they have to go through a gamma camera to then take a scan of where those white blood cells are conjugating to. As you can see in this picture, the anterior and posterior view of the patient. So those little black spots are where the Indium-111 and white blood cells are conjugating into. The dosing of this isotope is about 0.3 to 0.5 millicuries. It is a very safe dosing of the isotope because the recommendation of dosing is 7.4 to 18.4 millicuries. The scan itself is also very safe and emits very little radiation to the patient. The scan is similar to a chest x-ray or a CT scan.
Indium-111 white blood cell scan is important because it allows providers an inside look at where the white blood cells are gathering to inside of someone's body, which this allows the providers to find the possible origin of fevers, infections, and inflammation. This is very important as this helps create a treatment plan for the patient. The dosing for the isotope is very safe, and having a scan performed is equivalent to having a chest CT scan performed. Now we can take a look at the nuclear equation for Indium-111. You start with Indium-111 and it undergoes electron capture, where it absorbs one of its inner electrons, and this causes a proton to become a neutron. This is how we end up with cadmium-111. The cadmium-111 is usually left in an excited state, and when it returns to its ground state, it emits two gamma rays, as we can see in the equation. This is why the use of Indium-111 is so useful for medical imaging. Now we have an integrated rate law question. A patient is given 0.50 millicuries of Indium-111 to have a white blood cell scan performed. With a half-life of 67 hours, how much millicuries of the Indium-111 will be remaining in the patient's system after 88 hours? So we're given the half-life, which is 67 hours. So to find K, we would do 0.693 divided by the half-life, which is 67 hours, which gives you 0.010. Now that we have K, we can plug in the numbers that we know. So in the natural log of final over initial, we know the initial, which is going to be 0.50 millicuries. We can plug in the K, and then we can plug in the T or time with the 88 hours. Once we do all the math, which is shown below, you'll come to a final of 0.21 millicuries would be left in the patient's body after 88 hours. A millicurie is just a unit of radioactivity. And then here's our citations.